Okay, let's get started. So I want to do several things today. If I remember correctly, you have an assignment due later this weekend. So I want to open the floor for questions about that. Once we finish that, I want to go back to where we left off last time. There's still some points I want to make about assignment 1 and the various issues that arose, and then move on to sampling, and that probably will take us to the end of the hour. If it doesn't, then we can start looking at Spark. Otherwise, we'll start next week. All right? So on a point of clarification for number 6, in case you haven't gotten there yet. So basically on problem 6, I asked you to create what statisticians call a population, or a random sample of 100,000 integers. And then from that 100,000, we're going to take a random sample, right? And, then the question is, I know what the mean of that 100,000 is, right? And when I take that sample, I'll have its mean. And sampling theory will tell us that the mean of the sample should be relatively close to the mean of the 100,000 integers. The question is, how far away is it? So when I say, what is the error? I mean, the actual answer is the mean of the 100,000 numbers, right? And so how far away is the mean of the sample? And now the problem is to say it's 50 units or 200 units away is misleading, because if I then say I create a population of integers between 1 and 10, right, and I compute the mean and take a sample, that mean is much closer, but percentage-wise it could be farther away, right? So when I say error, what I mean is, look, find the mean of the 100,000, find the mean of the sample, and then what's the percentage error, right, that we have, right? Then in problem 7, right, well, the problem with number 6 is you do it once, and when you pick a random sample, you may pick a bad random sample, right? Maybe there'll be some probability when you pick that random sample of 100, you happen to pick just numbers that are less than the mean of the whole population, right? That could happen with a small probability. And so some people, when they do problem 6, they might get very close to the actual mean of that 100,000. And some people might, just by random chance, be farther away, right? Because you're just picking a random sample. So problem 7 is meant to sort of, instead of doing that once, let's do it 1,000 samples, right? And then I take 1,000 samples, and now I'm going to compute the mean of each one, right? So now I have 1,000 means, right? And then what happens is those means should have sort of a bell-like shape if you were to plot them. Again, there's a theorem that tells us what should happen, but the question then is, where are most of them? So let's see if I can do this. Right, so here's my number line, right? And so I'm plotting a bunch of, I have 1,000 of these x's, right? And they're going to be all over the place. And I won't do 1,000 of them because it's going to take too long, right? And so then but I know what the mean of the actual 100,000 elements are, right? And so let's let that be M. And so now the question becomes, if you know the words, I want to find the 95% confidence interval. That is the interval that when I start from the mean and go equal distance from it, I end up with 95% of the values of those 1,000 means we computed, right? And there are two ways you can do that. One is if we're statistician and we have the tools, we could then use some of the things we'll talk about in the sampling lecture. The other way we can do it experimentally. That is, well, go out y distance and how many elements are of that 1,000 are in that interval, right? And just keep on making y larger and larger and larger until you get 95%. And 95% of 1,000 is 950. When I ask you a simple question, you should take the opportunity to answer it, right? Because then it's a trap, right? And the goal is just to get an intuitive feel for, right, if my sample is 100 size, how big is that interval? When I now do it, my sample size becomes 1,000, presumably that the interval should get smaller, right? When I do 10,000, it gets smaller. Any questions? So in problem 6, you're gonna compute create a sample of 100,000 integers, right? And we're going to use that same input for problem 6 and problem 7, right? And then we're just going to take samples from that, right? Right, so in problem 6, you pick 100 random elements from that big array. Yeah, we want to pick a random sample, right? And what random means becomes important, because if you pick a sample which is not random, then you won't get the same result, right? This is, I don't know about India, but in this country, when we have elections, they continue taking polls, right, to figure out who's ahead or behind. And the theory tells them, basically, if you take a sample of a couple thousand people, you can be within a certain percentage of error, right? And what happens is they find that they're wrong, right? And the main reason they're wrong is you have to get a random sample of voters who actually are going to vote, right? And that's the hard part, because first of all, people don't know. They say they're going to vote, but it doesn't mean they do vote, right? Plus, it's hard to get a hold of everybody, right? How can you contact everyone? What you do is you get a list of phone numbers you can call, but that sample also may not be random, right? It may have some biases. It may be biased towards Republicans or Democrats or independents, right? So it's getting that random sample, right? And that is problem 5, right? How do we, given an array or a list of elements and a size, how to pick off, random elements in that array, right? In some sort of random fashion. Yeah, sure. Yeah. Yeah. Right. Right. Correct. So what is a higher order function? What's that? No, what is a higher order function? Anyone? See, that's why you should always answer the easy questions, right? Because if you answer the easy question and say, well, I already answered one question, it's someone else's responsibility to answer the next one. No one has any idea what higher... Yeah, a higher order function is a function that one of its inputs is another function, right? Does MapReduce a function? So a higher order function is a function that takes the function as argument, right? And the reason it's called higher order is because instead of acting on data, it acts on functions, right? And what's the input to a map? It's a function, right? What's the input to a map? It's a function. What's the input to a filter? It's a function, right? So those are, and again, the motivation for this is when we go to Spark, right? When you want to manipulate data, you get higher order functions. You don't get the for loop. There is no for loop, right? And the reason is with the map and reduce and filter and all the other higher order functions they give us, it's easy to take that and spread it across multiple machines. A for loop, for I equals 1 to n, that is really, really hard to distribute across multiple machines. So the goal of that requirement is to sort of give you a little more experience doing Scala and, no, you should know what a higher order function is, right? A higher order function is one that takes another function as an argument. Any other questions? What are the meaning of sampling without replacement? Let's say, I have 4 elements, A, B, C, and D, right? Now I want to take a random sample of 2 elements, right? So I pick a random number, oh, it's 2, so I pick up B, right? And now I pick another random number, and I happen to get 2 again. Well, so then my random sample is BB. That's sampling with replacement, right? I put the B back in so I can then select it again if need be, right? Sampling without replacement is, okay, I start with, I got 4 elements. I pick a random number, let's say it's 3, so I get C. And now what I do is I remove C from the options. And now there's no way when I get C again, right? So I don't want to without replacement means when I select an element from my original collection or population, I don't want to be able to select it again. Out of the list, right. Any other questions? So the question is, how do I compute R in problem 7? There's two ways. One way I'll sort of outline on the sampling note, and the other way is just experimentally. You thinking about that? Any other questions? Um, the array function receives a collection of strings and a map from strings to integers, right? So we have two inputs, right? One is this array with Tom, Fred, and Harry. And the other one, we have a map, right, which maps names to numbers. And so then what we do is, okay, Tom gets mapped to what? Oh, it gets mapped to 3. So 3 is in the output. Fred gets mapped to, there is no Fred, right? So there's no mapping for that. Harry gets mapped to 5. Oh, so the output has 3 and 5.
For number 4, for your input, how do you handle the map string? If I'm only counted as
I'm not sure what the question is in terms of, the question is, how do you create the map object?
I just create an array of parameter and parameter do the map. I feed it in an array and then the map. But then when I try to do string comment int, it only interprets the like when I try to feed in. Is there a different way I should be?
That's what I would think it should be, so I'm not sure what's going on.
I feed it in this, but then it will complain.
What type do they give it that? Yeah, you have to ask me. I mean, yeah. So let's move on. So last time we were looking at this question, we have numbers between 0 and max and value divided by 2. And we have a million of them. How much space is that going to take up on disk? Anyone? Yeah, I was hoping for a slightly more precise answer than a lot. What's that? How much more? So one answer is a lot, which is not very precise. Another one, isn't it just a million bytes? If we're storing it as a string, why 8 million? If I store that number as a string, how many bytes does it take? Right, so now how many bits does it take to represent a character? 1 bit? No. 1 bit? No. Is it 1 byte? How does Java store strings? Yeah, so if it's Unicode code, how are we going to store the string? Anyone know? Yeah, I'm going to convert it to a string, right? And I'm going to write it to a file. You did this. Yes, which encoding, right? So which encoding was used when you wrote your file for assignment 1? Okay, so if I use UTF-8, right, and I take the character 5, how much space does that take? No? Correct. So if we're doing UTF-8, each character in our number is going to take 1 byte, right? Right. Right. So to answer this question, right, we need, for each character in our number, we're going to take a byte, right? So we need to know how many characters we have to deal with, right? And so what we're really then asking is, what's the average length of a string between 0, right, and max int? how many characters are in max int? What's the largest number we can store in an int? What's that? 65,000? So so what's the largest number you can store in an int? It's 10 digits long, right? Well, when you divide by 2, you still get the largest number is still going to have 10 digits. Because the largest number is 2 something, right? Right. But in max, the maximum number is like 2 billion, right? And so int max divided by 2 is still 1 billion. And so the largest number we can possibly get is still going to have 10 digits, right? So then we have to worry about, what's the average length of numbers between 0, right? But that's going to be, it's not going to be a factor of 20, right? It's going to be a factor of 10. Why? Well, because the maximum we're going to get, the maximum size is going to be 10 digits. And each digit is going to take 1 byte, right? And then if we're going to put it on a single line, then we need 11 bytes. That's the maximum we're going to take, right? Other numbers will take fewer bytes. So the maximum expansion we get from going from binary to strings in that range is going to be a factor of 11, right? It's probably going to be less, but not much less, right? Because there are a lot more numbers between 999,999 and than there are between 0 and 1, right? What's that? There's going to be 9 billion bytes? Did you compute it? How? Okay, so that was 9 digits long, so we're going to end up with, 9 million bytes for the numbers, and then we need another 1 byte for all the new lines, right? And so, yeah, it's getting to be pretty big, right? And it shouldn't be 10 gig. But it also points out that there's expansion, right? And so if we were to store on disk as bytes, it's going to be much smaller, right? And that means it's smaller, it's going to be faster to read in because there's less data to read in, and it's going to be easier, faster to convert bytes into integers than it's going to be to convert strings into integers. That's right. The binary files are very painful because it's hard to see whether you did it right. And so you have to write the code to write the file and write the code to read the file. And if something goes wrong, you don't know which end was the problem, writing or reading. Yes, I've done this, and it can be fun if you make an error because you don't know which place you made the error. And then you start looking for editors which will allow you to look at binary And on Unix, there are editors that do that, right? Allow you to just look at the file in the binary format, and then you start having to go FFF this, right? But it's far more efficient. All right. Find the meaning of n integers. How do we do this? We've got a million numbers. So one way is a sort, right? What about this number? How would you deal with this? With a billion numbers, right? Right. Yeah, so the shifting of bits, that's an implementation detail, right? So let's say we've got numbers between 0 and 100, just to make it simple, right? And so what we're going to do is we're going to create bins. And so let's create a bin between 0 and 20, and then a bin from say 21 to 40, right? And then we go 41 to 60, and then 61 to 80, and I'm running out of room here. Another bin from 81 to 100, right? And then what we do is we read our numbers in one at a time, and we just count how many times the number falls in each bin, right? So maybe get one there, then one there, and get another one here, one there, and one here, and one here, and then maybe one here. You get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so that I'm done, right? And so I've got 4 numbers here, 3 numbers there, 1 number there, 2 numbers there, and 1 there. And I have a total of, if I did it right, I have 10 numbers, right? Let's see, there's 7, 8, 9, 10, 11. I thought I had 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10, 11. I need one more. Let's do 12. So now I get 4. All right. The median number of 12 numbers is going to be the 6th one, right? So the first 4 here, that median is not going to be in this bucket, right? Is it going to be in this bucket? These are numbers 5 through 8, right? Actually, somehow I got too many 4, 8, 9, 10, 11, 12. So it should be number 6, right? And so the median is going to be in this bucket, right? I'm waiting for some few more heads to nod up and down, right? So now I know it's in this bucket, right? And I know that there are 4 elements that go before this bucket, right? So in this bucket, I want number 6, right? So overall, but since there's 4 that come before it, I really want the second number in this bucket, right? So now I make another pass through my data, right? And what I do is, okay, I know this number 4, and I'm just interested in numbers between now 21 and 40, right? And I go through them. If I get a number outside that range, I don't worry about it, right? And I just keep track now. There's 21, 22, up to 40, right? And I just start marking what I may need to keep a count, right? Because the number may occur more than once. So I start all counters all to 0, and I go through my numbers. Any number outside this range, I don't worry about. When they're in this range, I increment my counter, and then when I'm done, I then start from the beginning, and I look for the second number that occurs, right? And that's going to be my median, right? So the algorithm you discovered is using these buckets, but they're making it efficient by doing this shifting of bits around, right? Taking the top half of numbers, that defines the number of buckets, and then you count how many they're going to be, find out which bucket's going in, right? And keep track of how many were before, and now we just look at those numbers in that bucket, right? Right, right. Yeah. But again, the algorithm, I can choose how many buckets I want, right? I could choose 3 buckets. I mean, the more buckets I start with, the sooner I get down to a smaller size I can actually do it. The algorithm they used was, again, being efficient and saying, look, I'll just take the first 16 bits of my number and use that to, each number is going to be a separate bucket. But the basic idea is I fix a number of buckets to work with and then count how many numbers fall in each bucket. And then I can then compute which bucket that median is supposed to be in. And I can keep on repeating that as many times as I want until I get down to, so if you want to do this for longs, right, that, taking the 16 top bits, maybe it's going to take more passes, right? But it's just basically a bunch of buckets, fill them up, find, and repeat, right? Again, the reason it's important is, right, we have to pay attention to algorithms, and we start getting larger things, right? What we naively tend to do may not work. And did I? What? 4 billion, right? Right. Bucket. We have to take a full pass, right? You're making multiple passes, right? It depends on how big your buckets are, right? I guess what I'm saying is, let's say Right. Right. Yeah, so why not just sort it? How long will it take to sort a billion numbers? But you also have to go over the space complexity, right? For example, if I had 4 billion numbers, how would you find the median? Well, what you did was you put them in an array, right? And you sorted the array, and then will 4 billion numbers go into an array? You know, I don't care what machine you're using, right? You know, Amazon has machines that have a terabyte of memory, right? So if I rent one of those machines, they have a terabyte of memory, and I'm using Spark, and either Java or Scala, can I put 4 billion numbers into an array? And if it makes it easier, they're going to come up with a machine soon that has 2 terabytes of that memory. And they claim within a year there'll be 4 terabyte machines, right? And it doesn't take 4 terabytes to store. How many elements can you put into an array in Java? You can only put about 2 billion numbers into an array in Java. Why? Well, because they use an integer to index the array, right? So once we go above 2 billion, all of a sudden we can't sort one array. We're going to have to use multiple arrays, right? Again, another barrier, right? That we come across when you start getting large things. Doesn't mean. Yeah, the question is tuple. I'm sorry, but the tuple sizes don't get anywhere near a billion. When you look at Scala, they cheat on tuples, and so they define a tuple class for each size, and so they can only go up like 16. So if you find a tuple larger than that, I mean, you have to make your own tuple. Lists, if we're talking about a linked list, that's different, but if we're talking about, we have to ask what they're backed by, and usually they back it by an array. And once you get anything backed by array, right? So it's just another barrier, right, that we cross. And you have to be aware of it. For this, I won't go through this algorithm. I'll just let you know it exists. There's this clever little algorithm that allows you to add numbers together. And the most interesting thing is, by normal sum, I mean, you just have n numbers, and you add the first, the second, and you add the third to that, and you add the fourth to that, right? You just go through sequentially. When you do that type of addition, the growth in the error rate is the machine precision of the machine you're using times the number of elements, right? So the more numbers you add together that way, the larger the error gets. It grows with n. If we do pairwise summation, right, you have a large number, you add them the first and second, the third and fourth, fifth and sixth, right, all various pairs. And then you go through again, you take those numbers and you add them by pairwise, and you keep on doing it until you get one number. The error rate grows at the machine rate times log n, right? It grows slower. This summation algorithm, its error rate is independent of the number how many numbers you're adding, right? Basically what you do is you add a number to the sum, and then you subtract it out again and see what the error is, and you take that difference and add it back in again. And that helps reduce that accumulation of errors. Right. This is again, I just want to emphasize, right? Space complexity, time complexity, we have to worry about because now we're looking at big things, right? Algorithms become important. And one way to deal with large numbers is not to deal with large numbers of data. Just take samples, right? Right, and there are a lot of times when, there's several examples here. If you got 1 billion numbers or 10 billion numbers, you want to compute the median. Do you need to know the exact median and mean, or can you have an approximation that'll be good enough? A couple of other examples of problems like this. One common one is, look, and Chrome does this, right? When you request a web page, right, Chrome wants to warn you when you're going to a known malicious site, right? But how many malicious sites are there? There's a lot, right? And so what they want to do is they want to check on your machine first, right? Because otherwise they don't want to check their servers every time. Because that would mean every time you went to any URL, you would have to first go to Google and say, is this a malicious site? Yes or no, and get the answer back. And then you go to the real site, right? And that would slow you down. So what they want is they want a quick check inside the browser, right, to say, is this potentially a malicious URL? If it is, then if it's not malicious, then we'll just go, we won't have to bother checking. But it might be malicious, then we'll go and check with Google to double check, right? But the problem is there's too many malicious sites to list in your browser, right? The list gets too big. So you want some sort of space-efficient way to answer that question. Is this URL malicious or not? The same thing happens in a web crawler, right? What does the web crawler do? You start up some known set of pages, and you go to each page, you look at the links, right? And you add those links to things you need to go to, and one by one you go to those pages, but eventually a page will point back to where you were before, right? And you want this process to stop, so you want to know every time you go to a web page, have I been there before? But Google indexes billions of pages, and so they want an easy way to tell whether in the middle of this process, have I seen that page before in this process or not. We talk about this, descriptive. Statistics have these ways of dealing with these things. Mean mode, when we're talking about this. So in statistics, right, we can talk about the variance, the standard deviation of numbers, quartiles, are you in the top quartile? We do divide the numbers into 4 different groups. And usually a quantile is like 4 different groups, and so we know what group we're in. So typically when you look at these sort of diagrams, the bars are going to indicate the the median value, and then they're going to give the quantile below median and above median, give you a indication of the range, right, things are going. Right, so it's giving you some information about these numbers, right, without having to know exactly all the numbers. Distributions, right, the normal distribution is very common. Lots of processes produce Gaussian distributions, and the central limit theorem says that, basically you can take a bunch of random samples and compute the average. You get something that approximates the normal. This is a graph of doing that, taking a bunch of samples and computing the sums. And the reason it's important is because what happens then is we can talk about, if you look at the mean and go up far enough, right, we're going to capture nearly all the items that occur, right? This is called the confidence interval. And when you see medical studies, they'll say this is significant to the p-value of p equals 0.5, which means there's a 5% probability that our result falls outside this interval, right? And actually, there's now a movement to say that's not big enough. They really should do not p.05, but 0.005, because, right? And so there's this confidence interval that, okay, with 95% are going to be within this range, right? And if you want 95%, it's basically a standard deviation times, right, 1.96. And there's different, if you want a larger, we get a larger interval, it's going to cover more of the elements, right? And there's more likelihood that we're going to be contain more elements, so fewer things are going to be outside, right? And so the question is, when we start sampling, right, if we want to actually sample our data and then compute numerics on our sample, right, we're not going to get the exact numbers we want. We won't get the exact mean. We won't get the exact median, but we'll be close, right? And the question is, how close will we get? And statistics mathematicians have proven that, right, the standard error we get from standard error from the actual mean to the sample mean, right, is the standard deviation divided by the square root of our sample size, right? And so if we want to decrease our error rate by factor 2, we have to quadruple the size of our population. And when people do this, right, we take a standard deviation and divide it by the square root of n. Once n gets into thousands, this error gets pretty small. Right? That's why polling people, they don't sample tens of thousands of people. They do hundreds or maybe 1,000, because it's right. The error rate becomes much, much smaller. And so there are times when you may want to, instead of dealing with the entire data set, you may take a random sample and then, right, deal with that. And if you're a statistician and work with one, they can tell you, look, we want a sample size of this particular amount to get within the right error range. Now, let's also play a role if we're dealing with streaming data, right? For example, Amazon continually gets a stream of orders all the time, and they're trying to then understand what's going on. There's not like you can stop their purchasing process and just say, okay, that's like what's happened so far. What you do is the data streams in and you take a piece of it and then analyze that, right? But then how big a piece do you want to analyze to understand what's going on now? Yeah, so in this case, well, we can actually do this computation to figure out how big this interval should be. So here I did a calculation where I had 100,000 integers, sample of 1,000, then my confidence interval was, 95% was actually fairly small, and right, the sample mean was 523, and the actual mean was 501, right? So we can actually use this information to figure out how big our samples need to be. What is Z? Z should be, like, the limit there. Z is, Z, you figure out what particular confidence interval you want. You want 95%, you want 98%, right? And so that's the Z value. Right, so in theory, we can, compute our confidence interval if we know the standard deviation, right? Later, when we're dealing with Spark, we'll be able to compute standard deviation. Scale itself does not come with the built-in library, doesn't come with standard deviation. There are math libraries for Scala which do, but we'll look at it when we do a Spark. So in this case, if you want to actually be within 10, it turns out you need a sample size of 39,000. And I actually did a random sample of 39,000, took 5,000 samples, and looked at how far they were from the actual mean. And you see most of them are indeed pretty close. Right, so we can actually use statistics to figure out this confidence interval, figure out how much data we want to sample. To answer the second set of questions, there's this thing called a Bloom filter. And these are very, very common. And it's a test to see whether an element belongs in a set or not. And the Bloom filter does not store the set at all, right? And what the Bloom filter does is when you build a Bloom filter for a particular set, when you ask, is the element in a set or not, if the answer is no, you're guaranteed that the element is not in the set. When you ask the Bloom filter, is this element in a set, and it says yes, then it might be in a set, but there are false positives, right? So an example of Chrome, what they do is they produce a Bloom filter, and the Bloom filter is on your machine, right, in the data for Chrome. And so when you have a URL that asks, is this URL malicious or not? And if it's, when it calls the Bloom filter and asks, does this belong in that set? If the answer is no, then Chrome knows that that URL is not a known malicious site, and there's no need to check Google servers anymore, so we can just go to that site directly. When the Bloom filter says this URL is in this set, well, it's likely that it is, but there's a certain probability that it's not. In that case, you can then check with Google servers to verify, is this really a malicious site or not, right? Because an example where getting approximate answers actually gives us something we can deal with. So types of errors, if you haven't heard it before, there's false positives, which means, your test says this is true when it's actually false, and a false negative is when the test says it's negative when it's actually true. So Bloom filters are very interesting. So you start with n bits, and they're all 0. And you start with k different hash functions, right? And what you do is, for every element in the set, what you're going to do is you're going to apply each of the k hash functions to that element and see where in the table it leads you and mark that 0 into 1. Right? So I have m equals 18, k equals 3, I got some element, and I then do 3 hashes, and I mark those, it goes from 0 to 1. Right? Then I can ask, well, does this contain y or not? And the way you answer that question is you apply those k hash functions to y and look at all the locations, right, where it leads to, and ask if those are all 1, then it might be in the set. If 1 or more is 0, you know it's not in the set. Why? Well, because if it's a 0, we never hash the location and mark it to 1. Why do we use more than one hash function? To reduce the number of collisions, right? Does it contain X? Well, all locations, right? R1 is X in the set. Well, it could be, but we don't know for sure. Why? Because if I added 3 or 4 other elements, some of them, we may have covered some of those spots from other hashes, from other elements, right? So, for example, I do Z, and it comes out here, so now I have a bunch more locations which are 1, right? And now when I ask, is Y in there? Well, the problem is these 2 hashes are the same place for X, and now the other one goes the same place Z did, and so we don't know whether Y is in there for sure or not. Why? Because I could have added Y, and Y would have marked all those as 1, but other elements could have covered it, right? Right? And so it's a clever algorithm because now, how much space does it take? Well, it takes, when you pick M, it takes that number of bits, not bytes, but bits, right? So the question is, how helpful is that, right? Well, let's look at the case of in Chrome, right? When you say go fetch this page, we want to know, is this a malicious page or not, right? And if the answer is no, then we just go directly. If the answer is yes, then we're going to do extra work to double check, right? How's that an advantage? Well, otherwise we either just always go to that page, or we always have to check, right? And so we're going to, most of the time, URLs are not going to be malicious. And so most of the time, right, we won't do any extra work. It's not wrong, but when you have that, when you're trying to crack a password, you keep the entire thing in memory, right? Here is we just want to have a quick test, and then we may have a follow-up check in the case when we get a positive. Yeah. Oh, so no, what you do is you have a list of all the malicious sites, right? And you create a Bloom filter on that, an entire list. But when you do that, right, you get to pick how big M is and how big K is, right? And so you have to figure out how big M, and to have M, be a couple thousand is not going to be a problem, right? Because we're just talking about bits, right? So maybe it's, 2,000. And that's going to give us, again, every once in a while Chrome will download that data and it'll check each time, okay, look. And most of the time we should get, if we pick M and K correctly, right, most of the time when we have a non-malicious website, they'll say, no, this is not in the set. There's various Bloom filters implemented for Scala. Here's one, and it's basically how many elements you expect in a set, what sort of false positive rate you want to get, and then it's going to pick M and K based upon that, right? So basically, say we want a 0.1% error rate, which isn't too bad. So places where they actually do this, Akamai is this company that caches network traffic all over the place, right? They have this content network. And the problem is, when someone accesses a page, do you want to put that in your cache or not? Well, there are a lot of what they call one-hit wonders. That one person will go to that page when no one else ever goes to that page. So why put it in your cache? It's just, the one person who's going to go to has already done it. So what they do is they only cache a page after the second time it's been accessed. But how do you know if the page has been accessed before, right? Without keeping track of all of them. That defeats the purpose, right? If you keep a full list of all of them, you might as well put them in your cache because you're already consuming the space. So they create a Bloom filter, right? Every time, right, someone accesses the page, right, they create a Bloom filter and add it to that Bloom filter. And now, when someone accesses the page, you go, is this in that set or not, right? And if it's not in that set, then it's the first time it's been accessed, so you just put it in the Bloom filter and do it else. If the Bloom filter says, yes, it's in that set, then you add it to your cache. There will be some times when you add a page, which the first time it's been hit, into your cache, but that's okay because it's not going to happen very often, right? So having an approximate answer almost always right is good enough. A lot of databases use Bloom filters, right? When you make a query on a table and you're looking for a particular row or a column, right? Actually, fetching that column or that row can be expensive because it's on the disk, right? So, for example, Postgres, when you make a query of Postgres, they keep a Bloom filter in memory of which columns exist in the table, right? So if you actually make a query that's asking for a column that doesn't exist, right, rather than fetching the table from disk and find it doesn't exist and then return an error, it checks the Bloom filter and says, oh, wait a minute, the Bloom filter says this column doesn't exist, right? And so they can return an error immediately without wasting time of actually searching disk, right? And if the Bloom filter does say exists, okay, then fine, I will go and I'll fetch the information from disk. And if it doesn't exist, well, sometimes it takes longer than it should to report the error, right? So there are times when having an almost always correct answer is okay, right? Right. Well, so in the case of a database, right, if someone adds a new column to the table, when you do that, you update the Bloom filter memory saying, here's a new element on the table. So you have an assignment due this weekend. On Tuesday, we'll start looking at Spark. So make sure you've downloaded Spark. When you go to the Spark site, they have some documentation, a quick start. You may want to start looking through that. In particular, you might want to try running the Spark, the scalar Spark. There's a REPL to play with. And if you're really ambitious, you can try accessing Spark from IntelliJ. I did spend 4 hours this morning making that work.